So today we are going to see mainly three advanced controllers. So there are six advanced controllers in your syllabus. We will start with what is the need of advanced controller. So if you just see the topic header is advanced controller, and what is the shortcoming of traditional controller for which we use advanced controller, that is supposed to be known first. And today we will see mainly three types of controllers, that is adaptive, model reference adaptive control, which is very much widely used in the vehicles. Adaptive controller is also used in the vehicle, and last type is robust control. So apart from there, there is fuzzy control. Apart from there, all these three, there is fuzzy control. There is model reference control or model predictive controller, and last one is optimal controller. So fuzzy controller, model predictive controller, and the last type, that is optimal controller, we will see in the coming lecture. So the traditional controller fell short to meet the ever-increasing demand for higher control accuracy, more stability, faster control action, and capability to control multiple input-output system parameters. So the first line itself says why these advanced controllers are required. So whatever traditional controller we have seen, so what a traditional controller, on-off controller, proportional controller, integral, derivative, PIPD, PID. So all these are very much traditional analog controllers. They are actually cannot produce very high accuracy as the controllers which we are going to explain now. For better system stability also we are using this advanced controllers, faster control action, capability of controlling multiple input output system parameter. So this multiple input output system parameter, this is called as a robust system. So this is one thing you can write down. What is meant by robust system? So robust system is nothing but multiple input output system, and how to control a robust system with high statistical dynamism, that also we will see in robust control. So hence the need for advanced controller technology surfaced in recent times. Different control paradigms such as adaptive control, model predictive control, robust control are proposed and successfully implemented for such purposes. So these adaptive, model predictive, robust, they all are called as advanced controllers. These controllers ensures faster time response with higher efficiencies and more robustness. More robustness means it can take care of multiple input, multiple outputs. These controllers allow the system to respond to a parameter variation and disturbances in a better and smarter manner. This results in small error, higher accuracy, and hence improves the overall system performance. So, in this first paragraph, mainly we have explained what are the better controller characteristic that is required from a system. There is high accuracy, high stability, smaller error, overall system performance improvement. All these are positive characteristics of a good controller. And these are the things where the traditional analog controllers were falling short. They were not robust. They were not able to control multiple input output variables. But whatever controllers we are going to discuss now, they can control multiple input output variables. So first we will start with adaptive controller, very frequently used controller in vehicles. So whenever the Bosch and the Mercedes, they had come here for a panel discussion, they asked us to include this adaptive control, model reference adaptive control, model predictive control, all these things in the syllabus. And these are actually control paradigms. So adaptive control comes first. So vehicle has to adapt to the unknown conditions. So whenever we are driving the vehicle on a road that we have not been before, there might come turn anytime. There might come some potholes on the road. Okay, there might be rain and all those things. There might be a traffic jam, or there might be open road, like you can take your vehicle to 150, 160 kilometer per hour speed. For every case, you should be able to adapt. to the bad situation as well as take the advantage of the good situation. So adaptive control is something where you don't know what is coming next, and whatever comes next, the vehicle has to adapt or adjust to those changes, okay, as soon as possible without losing the system stability. So this is the main agenda behind adaptive control. And for every controller, so if you are having pen and paper, you can write it down. That is for every controller, what all things we should know. So first thing is, what is the controller principle? That is the thing we are supposed to know. First, we are supposed to explain that. And second, we have to draw a block schematic. Okay, so block schematic diagram comes second. First is, what is the controller principle? Third is, after block schematic comes the blockwise explanation of function of every controller. Okay, so this is a third point. Fourth is the feature of the controller. Why this controller is superior or distinct from the other things. So first 4 point is, first is principle, second is block schematic, third one is functioning, fourth one is why this controller is distinct, or what is the special feature of this controller. So this is the fourth. Fifth one is advantage, which is somewhat related with the features. But whenever we are explaining feature, we have to explain both positive features as well as negative features. Some of the things the controller might not be able to do. Okay, so we need to have a further version of that controller or more variation in that controller to achieve all those positive points. So that is also, we should know that what a controller can do and cannot do. So there's the fourth point. Fifth point is advantage. Sixth point is limitation. Seventh point is very important. What are the application scenario? So under which conditions we are going to apply this type of controller to a particular application? So every controller is not applicable everywhere. So what is the scenario when the special kind of controller may be applied for a vehicular or automobile application? Very clearly you should write and then explain. So first you should write introduction, give the introduction and principle of operation, then circuit diagram or system diagram. Then explain, then functioning of the controller. Then comes feature, advantage, disadvantage, advantage or limitation, and finally application. So let us enter the field of adaptive control. It was heavily suggested by all automobile companies who had come in our institute while designing the AEL syllabus. They had said this controller must be known to all the AEL people. And obviously, the code for all these things you can find in Simulink, and you can do a mini project on this adaptive control based on Simulink or MATLAB. So adaptive control is a control method used by, so it's a control paradigm actually. Uh, so like feed forward control is a control paradigm. PID control is a controller paradigm. So adaptive control is also a paradigm. So this method is used by a controller which must adapt or adjust to the controlled system with variable and initially uncertain parameters. So there are a lot of uncertain parameters while we are driving the car. The vehicle should adapt to that. For example, an aircraft or spacecraft flies, its mass slowly decreases as a result of fuel consumption. So continuously the same thing happens in case of satellite also. As satellite keeps on going up, its dynamics keep on changing at every moment, at every second, because every second the satellite or the aircraft, they're using fuel. That means that every second the system is becoming lighter. So how can you adjust the speed so that you can achieve optimum efficiency from the engine? Okay. So a control law is needed that adapts itself to such changing conditions. Adaptive control needs a priori information. What is meant by a priori information? Which is there in your hand from the beginning. Okay. So a priori means, suppose in the summer time, whenever a cricket match is organized at some place in the evening time, maybe 3 o'clock the match is starting. So a priori information is around 7 o'clock. There will be a rain for 15 minutes in this ground. So before we are starting the system, we should know what all a priori information are possible about the system and about the whole control trajectory. So adaptive control needs a prior information, already known information about the reference model. So there is a reference model which will come in adaptive controller, and we should know this information about the reference model from the beginning and the range of uncertain or time varying parameter. So even if there is a change in the road or change in the condition and all, what is the range? What can be the worst kind of scenario when the situation is changing? Like I gave you the example of rain coming in the cricket match. So you should know at least for how much time the rain will persist. Whether it will persist for 1 hour or 2 hour or 3 hour or for 15 minutes. Okay, so whenever you are driving a vehicle, the road might be bad. The road might be bad means if it is very bad means you cannot drive it. So there will be a lot of gravels and all these things on the road, or road will be totally cut. You cannot go to the other side. Whether it will be like that, that you have to take a reverse turn and come back, or the road will be the texture or surface of the road will be bad. But yes, you cannot drive at the speed of 90 or 100, but maybe there is a patch of 2 to 5 kilometers. You can drive at the speed of 20 to 30 kilometer, and you can cover that 5 kilometer patch. So even if there is uncertainty, uncertainty is okay, but how much is the degree of uncertainty that is there? So like I'll give you another example that there is a lot of pay cut during the COVID time. Yeah, so pay cut is first thing not acceptable by the employees. So there is a pay cut, but employees should know how much would be the pay cut, whether the pay cut will be 50% or the pay cut would be 70% or 90%. So they can adjust all their system accordingly. Okay. So uncertainty is one thing, and the range of uncertainty is another thing, which should be known a priori to the system. So adaptive controller needs a priori information about the reference model and the range of uncertain or time varying parameters. So how bad it can be if it is bad, or if it is good, how good it can be. So adaptive control is concerned about the control law which are changing themselves as per the changing system dynamics. So vehicle dynamics has to change according to the condition through which the vehicle will be driven. That means road condition, maybe light condition, maybe rain will be there, or maybe traffic jam and all those things. So through all this, the vehicle has to adjust its performance. So very important line, adaptive control is concerned with the control law which are changing themselves. So control law is changing as per the changing system dynamics. This controller can modify its behavior in response to changes in the dynamics of the process and the disturbances. So disturbances, whenever you are driving a car, disturbance can be suddenly there might come some car in your way. Adaptive controller very fast should apply the brake. Okay, or we are driving and suddenly there might be a rain starting. So as soon as the rain starts, we should be able to switch on the windscreen of the vehicle, okay, as soon as possible. So these are the kind of scenarios which are actually followed in adaptive control. So this controller can modify its response or behavior to changes in the dynamics of the process and the disturbances. Main goal of this controller is to compensate for the parametric variations which may occur due to the nonlinearities in the actuators, changes in the operating process conditions, and time varying disturbances acting on the process. Three very important things. So what are the three things that we are supposed to compensate or we are supposed to adapt to? So first thing is we are supposed to adapt to the parametric variation which may occur due to the nonlinearities in the actuator. Okay, so everywhere in the vehicle, there between the controller and the process there is an actuator, but actuators are not linear. So that was a question asked in the exam. That is, what is the problem in driving? The problem in driving is with steering. So the rotation of steering and how much the car turn it takes, they are not always linear. If the speed is more at the time for the same rotation, your turn will be of one type. If the speed of the vehicle is less, in that case, with a turn of the steering, the vehicle rotation will be of different type. So main goal of this controller is to compensate for the parametric variation which may occur due to the nonlinearities in the actuators. So actuators are nonlinear. So for same input, it will not give you same output every time. It depends on all other related nonlinear conditions. Changes in the operating process condition, so which might suddenly add to a lot of disturbances, which might change suddenly, okay, and time varying disturbances acting on the process. So there will be some continuous time varying disturbances and there will be some sudden time varying disturbances. All these things should be compensated properly by the adaptive controller. So this type of controller maintains a consistent time performance in the presence of uncertain or unknown variations in the plant parameter. The same thing is said. So this type of controller, it maintains a consistent system performance. That means whatever may be the disturbance to the process, to the controller and all these things, but this controller would be able to produce a consistent system performance in the presence of highly uncertain or highly dynamic plant parameters. Now here, so below every diagram, you just write what is the diagram about. So this is called labeling. Here you can find the controller, here the plant and output. There is a feedback signal, so you can add a sensor here in the feedback signal. So all the things are same. So controller, plant, output, feedback, set point, all the things are same. Now, what is the special thing in adaptive controller? So you can see here at the top, just above the controller, there is a block which is called as parameter adjustment. So here you can apply those fancy controller paradigms, that is machine learning, deep learning, artificial intelligence. All those things can go for parameter adjustment. So the set point is given to the parameter adjustment block. Controller output is given to the parameter adjustment block. And controller output is nothing but proportional to whatever is the error output produced by the plant. So whatever is the error output produced by the plant, that is actually coming back, fed back to the controller input, and control signal MT is generated accordingly. So the same control signal whichever is going to plant, the same control signal is going to the parameter adjustment. So whatever is the error at the output, that is coming back to the controller input. Depending on that, to correct it, controller is changing its control signal. So that signal again is fed to the parameter adjustment block. And on the other hand, the set point is also given to the parameter adjustment block. So comparing these two, so how much is the error in the output for which controller is generating the control signal, and what the controller is trying to achieve. Okay, that is actually given in the set point. So the difference between these two actually used to change the controller parameter. Now, if you're talking about digital controller, this controller is nothing but an equation. It's a polynomial with some coefficients. So parameter adjustment means regularly we are going to update that polynomial. Best example, that a vehicle is running or aircraft or satellite is running and its fuel consumption is happening and the weight of the vehicle is reducing. So that is a plant. Weight of the vehicle is reducing. And whenever weight of the vehicle is reducing, actually you are feeling lighter. So the vehicle is feeling lighter. In that case, vehicle can run fast. So depending on the reduction in the weight of the fuel, controller should automatically increase the accelerator. Because for lighter vehicle to run fast, it needs comparatively lesser fuel than heavy vehicle to run fast. Okay, so that auto adjustment of the vehicle speed the controller can do. Okay, and whenever it is adjusting for the speed at the same time, it has to think for the provision of brake also. Because when the car is moving ahead with higher speed, higher velocity, at that time braking requirement also becomes more critical. Okay, so those things the controller has to look out. So now the controller is also being controlled. So this is the main important part. So what is the adaptation? The adaptation is happening in this parameter adjustment block. This parameter adjustment block is checking what is the required output and how much is the current output and whatever signal controller is producing. So depending on the set point and control signal by the controller, this parameter adjustment block is actually giving the command control parameter to the controller. So the whole controller polynomial is changing continuously depending on set point and control signal. And depending on that, the output also will likewise. So there's a very important thing to explain. So the explanation is given next. I will give you the this PDF. I'll give you the book links as well. Everything will be given to you. So an adaptive controller has mainly two loops. So you can find out one is the bottom loop, which is the feedback loop, and what is one is the top loop. That is, the controller is controlled, or the controller polynomial equation is controlled, or that is getting adapted to the stage-wise increment or time-wise increment of the overall plant dynamics. Okay, so this is control signal block loop. The top one is controller adjustment. So the adaptive controller has mainly two loops. One loop is a normal feedback loop, that is the bottom with the process plant which has to be controlled. The other loop is the parameter adjustment loop shown in the block diagram above. The parameter adjustment block is a distinguishing system block which has two inputs. So one is from the set point, the other is from the controller output MT. The controller, the control signal MT, which is mainly generated for the plant control due to some sudden disturbance, change occurs in the plant output. So if there is a sudden change in the plant, at that time the empty signal will also act accordingly to bring down or to nullify the effect of the sudden change in the plant action. So that is the job empty does. Hence, the output deviates far from the set point. So initially, if there is a sudden big change in the plant, at that time MT is not able to cope up with the sudden disturbance, so the output becomes too different. Output of the overall system becomes too different, and after 1 2 3 loops, okay, so that output very difference is big difference while output is fed back into the controller. Then controller actually generates the control signal MT. So after 2 3 loops, the transient actually subsides and the system again comes back to the normal control. But too much time it takes. So maybe 2, 3, 5, 10, or 20 loops of corrective action may have taken place in case of a pure feedback control. Okay. But in case of adaptive control, that thing will happen within 3 to 4 control loops. That is where adaptive control is superior. So it is written here, due to some sudden disturbance, sudden big change occurs in the plant output. Hence, the output deviates far from the set point. Here, a big jerk is experienced by the controller and a larger empty or control signal is generated by the controller. Generally, feedback controller, it happens. As a parameter adjustment blocks, so now they're talking about adaptive control. As a parameter adjustment block receives both the set point and the empty input. So parameter adjustment block is coming to know about the disturbance after one loop, that big change has come in the plant. That's why plant output has deviated very heavily, and that's why the controller is generating a big control signal. So that as the empty goes to the parameter adjustment block, and as the set point is continuously connected to the parameter adjustment block, the parameter adjustment blocks receives both the set point and empty input. It comes to know that system output has deviated far from the set point. Hence, control parameter signal to the control block input becomes larger. So in that case, the set point or the parameter adjustment block will tell the controller that whatever smaller control action you are generating empty, that is not good enough. So the parameter adjustment block internally adjusts its parameter in such a way that big amount of empty will be generated by the controller. So that is where the adaptation is happening. So as a parameter adjustment block receives both the set point and empty input, it comes to know that system output has deviated far from the set point. Hence, the control parameter signal to the control block input also becomes larger. That means empty becomes larger. So this brings down the error to a lower value faster and in a steady manner. So in case of feedback control, maybe it was taking 20 loops to bring down the error to zero or within a band. But in case of adaptive control, as the whole uh, control controller and whole process equation is changing, in that case, it is easier to bring down the error and bring the system to a nominal level. Okay, controlled nominal level. So it is to be remembered that the parameter adjustment loop is comparatively slower than the actual feedback loop. So obviously, actual feedback loop is the process and control around, so that is very fast. But parameter adjustment is a loop where the decision is to be taken, decision is to be made. Okay, and it is very slow. top loop is slow, bottom loop is very fast. So this can be a question in case of your, this can be a minute question or minor question in your interviews, that in adaptive controller which block is faster and which block is slower. So you have to say there are two main blocks. One is the bottom block, which is the controller process and there is a top block which is for the adjustment of the controller parameter. So in that case, the top block is actually a little slower than the bottom block. So it is written, it is to be remembered that the parameter adjustment loop is comparatively slower than the actual feedback loop. The control action is superior and smoother than the simple feedback control because in adaptive control, the controller has two reference inputs and the set point inputs. Now, there are three main approaches for designing an adaptive controller. Okay, so whenever you are asked with adaptive controller, you have to explain all these three, but don't go on explaining everything in detail. Just in short, whenever adaptive controller is asked, this explanation of MRAC, gain scheduling, self-tuning, all this thing has to be explained in short. These are the types of adaptive control. And MRAC can be a specific big question. That is, model reference adaptive control itself can be a very big question. Okay, for 10 minutes. So there are mainly three main approaches in designing adaptive control. First one is model reference adaptive control, then is gain scheduling and self-tuning. So let us find out what is model reference adaptive control. So it's a servo mechanism. What is meant by servo mechanism? We give some kind of error input and the servo rotates and it comes back and the error is minimized and the system comes back to the proper value for which it is designed. So it's a servo mechanism in which the desired performance is expressed in terms of a reference model. So you can find out that in the block diagram there is a reference model. Okay. So I give you the example that a parent is having two child, both are suppose brothers. So they teach the elder son very properly, and elder son becomes a model. Okay, his behavior, his attitude, his soft skill, and everything. So he is like a model student, model son. Now, when he is not at home, now there comes a plant, which is the younger son, okay, and who is not that well behaved and all. So, what the parents would tell him, parents instead of controlling, the parents would keep the ideology of the elder brother in front of him. So, they would tell the plant or the younger son to be like the elder son. And the younger son plant has seen the elder son reference model. So, the plant would try to be, or plant would try to uh, uh, behave or follow the reference model. So there are actually two equations. Plant is also an equation with polynomials and variables. You have seen what is meant by load variable in case of that water bath experiment, which was explained in this chapter. Okay. So plant means there are some loading parameters and all. Controlled variable and controlling parameter, all those things are there. And reference model also will be having them, but reference model is a ideal model. And what will eventually happen is in this, the controller would take this plant to this reference model, and that is the final convergence. So how it happens, we will see in the model reference adaptive control. Okay, so let us see the MRAC. So this is another thing which is very much required in the vehicle. So this thing is also has to requires understood, well understood, while we are doing a vehicle kind of adaptive control, vehicular adaptive control. So the main adjustment mechanism block is the heart of the MRAC system. So what is that? So previous case there was a parametric adjustment. In this case also there is a adjustment mechanism. Okay. So here it is written, you can see the top, that it contains a plant whose parameters are unknown. So this is the plant whose parameters are unknown. So this is the younger son, okay, who is uncontrollable. So a reference model for compactly specifying the desired output of the control system, an ordinary feedback loop, and an adjustment mechanism or adaptation control law. So this reference model is like a thing to be followed by the plant. Okay, the plant is not behaving properly, but the controller and adjustment mechanism together, they will make the plant behave like the model. So this is a reference model equation here in the reference model, and finally we say that the process is converging. The process is converging means this plant is actually behaving like the reference model. So that will be the end of the model. Has the plant is completely converged. Means what? This plant is now totally behaving like the reference model and perfect. Stability wise, some kind of randomness wise, everything is perfectly controlled. So the ultimate aim is the plant has to be like this reference model. So the adjustment mechanism block is at the heart of MRSA system. It takes three inputs from the system. You can check this adjustment mechanism. So first it is taking the input from the reference model. Second it is taking the input from the MT, and third it is taking the reference from the output. So this is one thing you have to explain. So adjustment mechanism block is at the heart of MRSA system. So you can find that below. This is the same feedback signal block. There is controller, plant, output, and there is a sensor and transducer and feedback, like I said. Okay. So this controller, plant, and feedback. This is the basic control loop. But above is a process where this controller also is being controlled by the adjustment mechanism. And adjustment mechanism is the brain of the whole process. Okay, so this is a bigger brain, and this is a global brain adjustment mechanism, and controller is a local brain. Controller is just controlling the plant, but who is controlling the controller? That is actually the adjustment mechanism. Okay. So the adjustment mechanism of MRSA system, it takes three inputs from the system. The idealistic system output, that is the main output which is coming from the plant, and it defines what should be the ideal rise time, settling time, overshoot, equivalent frequency domain characteristic, etc. So whatever is the output coming from the plant is like this. So this output you can see to the right side of the adjustment mechanism. This is actually telling us about the rise time, settling time, overshoot, and equivalent frequency domain characteristic of the output parameter. Second block or second input to the adjustment mechanism is the current plant output. Okay, so controller is controlling the plant. So whatever entity is generating, this is coming at the input of the adjustment mechanism. And the third thing which is coming from the reference model. Okay, so these are three things which is coming at the input of the adjustment mechanism, and adjustment mechanism is giving its output to the controller only. So I told you that the adjustment mechanism is like the kingmaker. So controller looks like the king, but adjustment mechanism is the person who is behind the screen and who is actually directing the controller how to work, how to behave, so that the deviation that has occurred in the plant due to disturbances, it will be minimized and will be brought back within the proper level as soon as possible. This is the main goal. So the current plant output, that is the first second thing. Idealistic system output. So I'll tell you this thing. Idealistic system output is reference output. From the reference model, it defines what should be the ideal rise time, settling time, overshoot, equivalent frequency domain characteristic, etc. So reference model output is kind of a standard. It is setting a standard how the output of the plant should be. And second is the current plant output, that is this. So this output should be actually like whatever is coming from the reference model. And third one is whatever is the difference between these two, depending on that the control signal is being generated. Here you can see the set point is connected not to the adjustment mechanism but to the reference model. So with the set point input, how the reference model is functioning, that we should know. So the adjustment mechanism block analyzes these three inputs and generates a signal for the controller. This adaptation mechanism is designed to guarantee the stability of the control system as well as the driving and the tracking the error to zero. The controller is usually described by the number of adjustable parameters. So how many parameters we are managing, how many parameters we are measuring or controlling. Okay, so this is very important feature or characteristic for the overall MRSA system. So the controller is usually described by the number of adjustable parameters. Existing adaptive control design normally require linear parameterization of the controller in order to obtain an adaptation mechanism with guaranteed stability and tracking convergence. So design of MRSC involves three steps. The first step in the MRSA design is choosing a control law containing the variable parameter. Second is choosing adaptation law for adjusting this parameter. So choosing a control law containing variable parameters and choosing an adaptation law for adjusting this parameter. And third one is analyzing the convergence process of the resulting closed loop control system. So we can apply this ML machine learning kind of a thing here. That is deciding the control law and deciding the adaptation law for the parameter or for minimizing the variation in the control output. So main feature of the adaptive control. So far we have been explaining adaptive control only. So MRAC is also an adaptive control. So other two parts I'm not explaining here, but whatever note I prepare, I'll give it to you. Gain scheduling and self-tuning. What are they? So self-tuning we have seen somewhat in the last day. Whenever we were talking about PID tuning, so how to set the value of KP, KI, KD, and what are the interrelationship between them. So that is kind of a controller tuning. So that was a self-tuning method for PID control. Okay. So now main features of adaptive control, why one should go for adaptive control. So that is an advantage. So variation in the process dynamics or process parameters may vary due to nonlinear actuators. So this very frequently this point is being emphasized. That is the actuators are nonlinear. Hence the controller should be so sudden change in the operating conditions of the process and non-stationary disturbances. So any disturbance come at any time. Suddenly there might come too many traffics. Suddenly there is a rain. Okay. In those cases also suddenly the road is damaged. In those cases also the vehicle should perform very well. So non-stationary disturbances acting on the process to compensate all this process dynamics, adaptive control is required. Second thing, to compensate for the variation in the character of disturbances. So even if the vehicle itself is behaving in a or misbehaving or it is not behaving in a proper manner, so there is a so it's a time varying system model. In that case, if there is a variation in the vehicle parameters, suppose suddenly the brake is not functioning properly, or maybe accelerator is not functioning properly, or maybe some sensors in the vehicle has gone bad. In those cases also that compensation should be done by this controller itself. So to compensate for the variation in the character of the disturbance of the vehicle itself to ensure the control accuracy and the system efficiency. So accuracy of control should be there and it should take place very fast. So this is the difference between feedback control and adaptive control. So feedback control takes quite a lot of time to bring the parameter into rest. But this adaptive control very fast will bring the parameter to rest and make the system stable. So it will increase the system efficiency, it will control the accuracy, and it will reduce the error very fast. That is actually advantage of adaptive control. And adaptive control are designed to control nonlinear and time varying process as well. So these are the special features of adaptive control. Then limitations, complex process, obviously that block, that is parameter adjustment block, it is a kind of a decision making block. So you can say all this decision can be done in cloud. So we are in the age of cloud computing. So Planet, there is a very vehicular ad hoc network. It is throwing all the data directly to the cloud, and the decision is being made to the cloud, and the controller in the vehicle is being asked to work accordingly. So this can be a very good project, or you can do some papers on this. That is how the vehicle data is going to the cloud. Cloud is making the decision, and vehicle uncertainty is being controlled as per that. So this is a very smart kind of a control. So complex process which requires a general model or structure. So what we are doing now is what are the limitations of this adaptive control. So complex process which requires a general model or structure of the plant. So controlling that very complex process controlling cannot be done by adaptive controller. The parameter adjustment process is slow and hence the control loop becomes slower. So that is what once again it was explained initially that the process loop, that is controller process output feedback. This loop is comparatively faster than the parameter adjustment process. Hence, the slowness of the parameter adjustment process makes the control process also slower. This is possible. If the plant is very big, then only this kind of problems occur. The use of high gain controller affects the stability of the closed loop system. So how do we know we are using high gain controller? So we are telling that normal controller can bring the error down to zero after 10 to 20 loops. Okay, but this adaptive controller can bring the error back to zero within maybe 5 to 10 loops. So I had shown you two graphs, KP with higher value of KP with lower value of KP. Okay, proportional controller with higher gain, so we are having a steeper curve, and proportional controller with lower value of KP, so we are getting a flatter curve. A steeper curve means KP value is higher, and the slope of the curve, if it is less, in case of proportional controller, means it was a slow converging controller. So exactly the same thing here. The use of high gain. High gain means steeper controller. So convergence will occur very fast. Error minimization will occur very fast. So as the gain of the controller increases, stability of the overall closed loop system decreases. That is what is told here. The use of high gain controller affects the stability of the closed loop system. The analysis is quite complicated, so that's why it is told that send the data to the cloud, let the analysis happen in the cloud itself, and after analysis the execution order has to come from the cloud to the vehicle, and the vehicle will be controlled accordingly. So analysis is quite complicated, time consuming, resource consuming. So whatever power and all these things are there in the vehicle's ECU, that also will be consumed at a higher rate. So different approaches for different needs, no general theory for common control. This is a very good thing actually, instead of bad. This is a good thing. So for a very specific car in a very specific terrain, so suppose you are going on hill, or you are going on the highway. So or maybe two different cars are going in these two directions. So for two different car going in these two directions means all four uh, control or driving features or profile will be different. And for all these four driving profiles, there will be different control action which is required from the adaptive control. So that is what is said is different approaches for different needs. So car may vary, the road condition may vary, daylight, light time may vary. Okay, rain might be there and might not be there. All those things. So whenever there is a different type of road, very new, innovative, proper, different type of control scheme has to be devised for that. So not same general rule for all vehicles and all road. That is not the case. So yes, different approaches for different needs. Very important. Application of adaptive control. Exactly the application feature or application scope where the adaptive control may be used. So application of adaptive control is found extensively in three main areas: aircraft control, industrial process, and electrical drives. So in EHV, that is electrical and hybrid vehicles, we can use this kind of adaptive control. So in the aeronautical field, where pioneering work on adaptive control was carried out, relatively few applications have been achieved on account of competition to rival techniques such as air data scheduling, and also due to the deficiencies in the basic adaptive control theory. So what it means is, though aeronautical field is the pioneer in deriving or designing the adaptive controller, but other fields are making better use of adaptive controller. The industrial field of application includes the cement industry, the steel and metallurgical industry, chemical industry, paper industry, power plant in some miscellaneous areas of process industry, etc. The main reason behind application of adaptive control to all these industries is that the complicated dynamic nature of the industrial process, as well as the conservative management of many industrial processes. So the main reason behind the application of adaptive control to all these industries is the complicated dynamic behavior of the process. So if the process become complex, and we don't know what is the future dynamics, and if the dynamics is within the range of the process, we use adaptive controller. So first is, whenever there is a more complex process, we use adaptive controller for better control, and the conservative management of many industrial process. So they have uh, put adaptive controller long back in their system, and now they don't want to change it. So that's why adaptive controller is staying there. So the field of electrical drives seem to be one of the most promising areas for the application of adaptive control. So whenever I am saying electrical drives means it is EV, EHV. So that falls in your domain. So the field of EV and EHV is one of the most promising areas for the application of adaptive control. So the dynamics of such systems are well understood and limitations of theory are less restrictive. That means adaptive control is more or less very well understood and very well documented theory, research, all those things are there. So you can go on applying this adaptive controller with lot of backup or with lot of back support. You can go ahead and apply adaptive controller for your system. That is the first type of controller. Actually, in that we have explained two different controllers. One is predictive, and second one is model reference adaptive. So I will send you the book. You prepare the question for adaptive for 10 marks. In that case, you have to explain MRAC also, gain scheduling also, and tuning also. And then only on MRAC, so only on model reference adaptive control, only 1.5 pages given. That will not suffice. So a big answer of model reference adaptive control you have to prepare for 10 marks. And I told you how to prepare it. So first is introduction, block schematic, functioning, feature, advantage, disadvantage, and or application. Sorry, limitation, and finally is application scope. So all these things you have to prepare. So for 10 marks, you have to write 3 pages. Okay. Then after adaptive control, we are going to another type of controller used in modern control theory. So I don't think I'll be able to control it, but at least let us have the initial understanding. This thing is called as MPC, or it's called as a model predictive control. Book is there, I'll send it to you. So it's an advanced method of process control that has been in use in the process industries, chemical plants since 1980s. So in recent time, it has also been used in power system balancing model. Model predictive controllers rely on dynamic models of the process. So continuously, the model is changing. Continuously, the process model is changing its nature or changing its dynamics. In that case, the controller has to predict what might be the model of the process now, and depending on that, the controller has to generate the control signal. So this is a little difficult. A lot of estimation, statistical things are required, but model predictive control is also a very popular and widely used control paradigm. The model predictive control, so in recent years, it has also been used in power system balancing. Model predictive control MPC rely on dynamic models of the process that is going to control. Most often, linear empirical models obtained from the same identification or system identification. The main advantage of MPC is that it helps to optimize the present system performance while keeping the feature of the system in account. So whenever it is model predictive control, first it understands the process, then it understands the controller, then it checks what is the compatibility between these two, and it always takes care of so present system performance while keeping feature of the system parameter in account. So what is the system feature? What is the controller feature? And whenever the system changes, then how the feature of the controller changes. All those things are kept into mind while the predictive controller is controlling the process. PID and LQR. PID, we know LQR is linear quadratic regulator, do not have this predictive ability. So always this is kind of predicting. So this is kind of a, you can say, feed forward kind of a thing, that it is going to predict what's going to come next. Okay, and depending on that, model predictive control is going to work. So MPC is a type of digital control. So previously, whatever model reference adaptive control we have seen, this was mainly, initially it was analog controller, but yes, now the digital version of the same thing is happening, is there. But this predictive control itself is a digital type of control. So MPC refers to a class of computer or control algorithm that utilizes an explicit process model to predict the future response of the plant. Okay. So in this case, a process model is required with us. So in the previous case, model reference adaptive control, we had a ideal model of the system. That was one thing. So the plant was trying to catch up. Plant was trying to change itself so that it can become ideal. So that was model reference adaptive control. In case of MPC, that is model predictive control, here the class of computer control algorithm utilizes an explicit process model. You can find here. Okay, so this is the process model. Okay, so here is the control. It is a controller, and controller is controlling the process. So signal given to is empty, and this process is trying to behave same as the model. So here, this process is actually trying to be the model. So MPC refers to a class of computer control algorithm that utilizes an explicit process model to predict the future response of the plant. Okay, so this output will be predicted, or this output is going to be as predicted by the process model. So at each control interval, the MPC algorithm attempts to optimize future plant behavior through computing a sequence of future manipulated variables. At first, an optimal means best control and performance characteristics. So initially, a best optimal sequence is set into the plant. Okay, so there's a plant or process that is given into the plant. So at first, a best control and performance characteristic sequence is set into the plant. Then at every consequent control interval, the entire control parameter calculation is repeated to achieve this optimal control. So initially, whenever we are giving this, after that we are trying to find out what is the best way to meet that. Okay, so whatever best control and performance characteristic is defined in the first place, in the second step, the every consequent control interval, the entire control parameter calculation is repeated to achieve the optimal control. So it was mainly developed to meet the control specification of power plants and petroleum refineries. MPC application is now found widely in use in variety of applications such as chemical, food processing, automotive, aeroplane, etc. In recent years, the MPC algorithm has been improved significantly. This has been possible due to the invention of faster computers. So obviously, like other controllers also, the inclusion of computers, it has made the process better. So this is the block diagram of model predictive control. So I'll just explain this thing in brief, and that will be it for today's session. So next session we might have on Thursday, or I might record a session and upload. So what's happening is this. So this is the control calculation. So control calculation is, again, there is something called a set point calculation. So this is set point calculation. So set point targets are decided by this. So whatever is the output between this model and process. So these two are being uh, continuously they are tracked. So this much is the output, and this is the output of the model. Okay, and difference of that is the deviation from the ideal output. So ideal output is given by the model, and process is actually creating output for any set of input. So process output and model output, that difference is actually the residual. So residual is nothing but the deviation from the actual uh, model of the process, a good model of the process. So this residual has to be finally minimized to zero. This is the main agenda. That process output and model output should be same. That's why the residual should be ideally equal to zero. So this is how the model predictive control work. The main aim is to residual has to be made as zero, and as long as the residual is there, prediction will be there. So predicted output is given to the set point calculation. So whatever predicted output is there, as soon as that is given to the set point calculation will generate some control instruction for the controller. And those control instructions are coming to the controller. Here the control actions are being again taken, and it is being sent to the process. So whatever process output is there, that process output is actually measured with respect to the model output. So model output is the ideal output, process output is the output with error. Depending on their difference, or depending on the residual amplitude, the prediction happens. And the prediction actually is helping the controller to change its parameters. And after, with every changed step of the control instruction or control calculation, the process output is going to be brought down with the error. So this is what is a model predictive controller. So when I upload this details, you can find it in your, you can just go through and find it what it is. So today I will upload the books as well as this note. Please check in the Google Classroom. That's all from my side. Thank you.